we have today. My name is Jim Satzinger. I'm the AIA Oregon Bend Section Director. And attendees, this program is being recorded. Please mute your audio and discover on your device the raise hand button for the question and answer period. AIA Oregon Digital Design Series continues. Coming next Thursday, May 20th at 5 p.m., AIA Oregon presents Bruce Ritchie, AIA Medford, with the Camelot Theater Project, Guggenheim Architecture and Design Studio, Jeff Guggenheim, AIA Portland, with the, let's see what it was, the Christian Church in, I lost a line, I'm sorry, Jeff. Balance Architecture, Rex Prater, AIA Eugene, the Oregon Imaging Center, hosted by AIA Oregon Small Firm Exchange, One Learning Unit HSW. Coming Thursday, June 3rd at 5 p.m., AIA Oregon presents Paul Baker Laporte, FAIA, Ashland, Nature is the Gold Standard for a Healthy Human Environment, 1LU HSW. Coming Thursday, June 10th at 5 p.m., AIA Oregon presents West of West, Clay Taylor, AIA, the Wells Fargo Tower renovation, the largest or the tallest building in Portland, 1LU HSW. And now today's AIA Oregon Digital Design Program, the In Process Lecture Series, hosted by Ben Arico, AIA Portland. Ben grew up in Corvallis, Oregon, and went to film school for his undergraduate degree at the College of Santa Fe, New Mexico. While studying film, Ben learned how the cultural identity of time and place manifests itself in the film medium. In many ways, these messages are subconscious. As he was completing his master's degree in architecture at the University of New Mexico, Ben saw striking similarities in the way that architecture speaks to us through the boundaries and facades of our environment. He grew to appreciate how our environment is not just designed by architects, but that our community creates architecture as an expression of itself physically, emotionally, economically, and socially. We get to see who we are by what we make space for. And now, Ben Arico, AIA.
Thank you, Jim. And thank you to all of our guests for joining our first in-process lecture series in the virtual space. I know that we all miss the free wine and beer that we had at the Center for Architecture in Portland and the in-person connection, but this format does have several advantages. Probably the best one is that we are getting guests and participants from all over the state rather than just the Portland area. So we're really happy that we have such a large audience here with us today, and we're excited to share our program with you. The focus of the In-Process lecture series is about how design develops. So we're not as much interested in the finished product as we are in hearing about design methodology, the tools used to study design, how design iterations work, how design interfaces with the realities of budget, schedule, client. So this is sort of a behind the scenes look at what really happens during the design phase of a project. The In-Process series works by pairing an architect and a trade partner. By trade partner, we mean somebody who works in a design field other than architecture. In the past, trade partners in this lecture series have been sound designers, furniture fabricators, photographers, ceramic artists, etc. It's great to hear two different perspectives on the field of design. And normally in lectures past, the architect and the trade partner don't have an immediate connection. However, this is a unique lecture because the architect and the trade partner literally collaborated on the same project, and they're going to share that story with us today. This joint presentation will last around 45 minutes, after which we'll have a 20-minute Q&A session. At that time, I'll be taking questions from the audience, so be thinking about what you'd like to ask. Part of this, what makes the In-Process lecture series so cool is that we really get into a free-flowing conversation at the end of the series, and there's a great dialogue between the community and the presenters where we talk about the ideas that we're generated during this show. If you'd like to put a question in the chat box throughout the presentation, go ahead and do that, and I will be reading questions from the chat box during the Q&A session as well. As Jim mentioned, we're going to try to use the raise hand feature as part of the Zoom functionality. If you can find the raise hand button during the Q&A session, that'll work as well. I would say that for the best experience for this lecture, go ahead and put your functionality on speaker view so you can see the speaker while you're seeing the screen. Now for our presenters. Tonight, our trade partner is Lyle Keck. Lyle leads the performance group for Affiliated Engineers, Seattle and Portland offices. Lyle's work involves simulating building performance and analyzing building systems. He looks at hospitals, laboratories, and higher education buildings, implementing advanced heat recovery systems, radiant heating and cooling systems, and all kinds of other energy conserving operational strategies. Lyle enjoys transforming these simulations into useful graphics and metrics that support design decision-making by project teams. Our architect presenter tonight is Scott Mooney, a lead designer and senior associate at SRG Partnership in Portland. SRG is a multidisciplinary firm with a focus on civic, higher education, science, healthcare, athletics, and workplace projects. Scott's career has been focused on both design excellence and environmental stewardship. In addition to his work at SRG, Scott has taught design studios at Portland State University, and he currently serves as a fellow in practice at the PSU School of Architecture's Center for Public Interest Design, where his pro bono efforts include work on emergency intermediate housing solutions to address our ongoing homelessness crisis. Please help me welcome Lyle Keck and Scott Mooney.
Great, thanks, Ben. That was a great introduction. And thanks so much to the AIA Oregon for inviting us to be a part of this lecture series. We are also a little bit bummed out that we don't get to interface with audience members in person, but you're right, the potential reach and impact of the conversation, I think can be quite powerful and meaningful, hopefully. We're looking forward to a robust conversation following the presentation. So a little bit about SRG. Our ethos is sort of leading with ideas that impact our shared future in a positive way. If you look at our work, we have offices in both Portland and Seattle. They really are derived from a strong conceptual framework, and that concept can come from any number of places, as most good architecture does. It's informed by our communities, by our cities, by the people who live and work in these places. And we try and create those high concept designs for any and all projects that we do, regardless of the size, regardless of the budget, regardless of the client. And we also want to make sure that those big ideas are rooted in performance, and they're really rooted in this rigorous study, this rigorous examination, research around the performance and sustainability impacts of those decisions. And finally, we just really excited to create wonderful places for people. We want to create environments that inspire, environments that really folks are happy to see as a part of the place that they call home, and really help create that positive impact on the communities in which we build.
Real quick intro on AEI, Affiliated Engineers, is a consulting engineering firm. We have about 700 staff across 17 offices in the US. Our main markets are healthcare, science and technology, and higher ed. So we typically work on more complex and high performance projects with a bunch of campus and institutional clients across the country. Next slide. So as Ben mentioned, I lead the building performance practice for both the Seattle and Portland offices. And our group focuses on energy and carbon analysis, water modeling, the occupant environment, and resilience. And we really work at the planning, design, and operation stage of these types of high performance projects.
All right, thanks, Lyle. And when we were first invited to be a part of the In-Process lecture series, we kind of thought about different ways that we might structure the talk, but really it came down to the best way to describe our process is to walk through a case study that shows that process step by step, and just sort of the level of consideration that goes into every decision we make as architects for a project. And so this one that we're going to talk about today is the OSU Cascades Academic Building 2 for Oregon State University in Bend. The work you're going to see today was a result of a really, I think, incredible collaboration between a number of very exciting partners that we were able to work with on this project. We ourselves at SRG Partnership, in particular, I want to give a shout out to the project team: Carl Hansen, Lisa Pedersen, Lori Canup, Emily Wright, David Webb, Jenna Bird, and Jim Wilson. But we had some amazing partnerships in our consultant teams as well. AEI, Swinnerton, the contractor, Swift, who's responsible for a lot of the landscape design that you're going to see early on, Katina, who really helped us do a deep dive on the embodied energy piece, and then our electrical consultant, Samata, and the other folks that you see on the screen. And so just to give everyone a quick overview of what we're going to talk about today, we're going to start with the landscape. What does it mean to design for a high desert campus? The massing, how does the architecture respond to that place? The structure and enclosure, how are we looking at that through the lens of the decarbonization priority that we have as architects and designers? Systems and operations, how are we going to get to net zero for this project? And finally, looking at the public spaces in the building and how do we make sure that those places stay simple and respond to the sort of inherent beauty that you see in mass timber structures. And so starting out, I'm assuming that we have a mostly Oregon audience, so I'm not going to try and place this in the world. I feel like everyone understands the Pacific Northwest. And the project that we're talking about today is in Bend. Bend, Oregon, for folks who have been there, has downtown in the upper right here. This is the Deschutes River kind of winding through the city. And the area that we're really going to talk about today is over here on the lower left, on the west side of town. This is a site that has been a sort of liability to Bend for a long time because it's an abandoned pumice mine and an abandoned landfill. And so the exciting opportunity with this, and I think the really incredible effort that's been made by Oregon State, is that they purchased this land and envisioned it as a future campus in Central Oregon. And so really transforming it to a really ambitious new campus that has public-private partnerships and is target net zero energy and net zero water as it's built out over the course of the next 20 to 30 years. And the building that we're going to be talking about is this one right here. It is the first of a whole new set of structures that will define the heart of this new campus, the oval green that will line this pumice mine that is carved into the earth in this part of town. And so the project goals, when we were going into this project, were quite exciting, but also a little bit intimidating. They wanted to set the tone for the future campus. They wanted to make sure that this project was flexible and adaptable, a good prototype for future buildings, that it incorporated a meaningful use of mass timber, that it was net zero energy, and all of this on what is a fairly aggressive budget for a higher education project. But before we talk about the building, we really want to talk about the place. If you think about Oregon State and the history of Oregon State, they had this beautiful campus in Corvallis that has a very formal and traditional campus plan with these campus greens. And that as a typology is really strong when you look at different types of campuses throughout the country and even the world. But when you go to Oregon, or when you go to the Central Oregon and you look at the landscape of Bend and the landscape of the high desert, it's a very different feel and it's a very different character. There's a rawness to it, there's a ruggedness, there's a sort of beauty that is different than what you would find sort of where a lot of us live down in the Willamette Valley. And then finally, the site itself, which is really a man-made landform in a lot of ways. It's the remnants of this almost violent intervention into the earth, but in a way it has a sort of raw beauty as a result as well. And one of the more interesting and I think inspiring aspects of this pumice mine as it sits today is that you've been able to see over time nature kind of take back over that space. And so how could we dovetail into that effort to restore and kind of reclaim this space? And so looking at those three kind of forces in concert, we took the existing kind of long-range development plan where we had this oval green and where there was intended to be this sort of bucolic amphitheater, and really challenged that notion a little bit and said, what if we start to take some of that high desert character, some of that ruggedness, and pull it into that space? And so that this building becomes almost an inflection point between the natural landscape and this more formal campus that's being developed for the future. And that really was an inspiration to us. And before we even got to the building, we really studied what that transition might look like, what that transition might feel like. On the upper left is really taking cues from the natural landscape, the natural erosion, the natural landforms. And on the right is thinking about the actual act of excavation. What does the quarry look like? How do that terracing work? You know, how can we kind of evoke the memory of this place and not try and bury it, but really embrace it in a meaningful way, so that folks can understand the history a little bit of the place that has become this campus for the 21st century. And so that's what you're seeing here, the kind of brown being the notion that this high desert landscape then sort of have this gradient down into this more formal campus green that's envisioned to be the heart of that future development. And then from there, we really wanted to understand how can that move really be a part of the building itself? How can we blur the edges between that indoor and outdoor environment? And how can the tectonics of the building really be in deference to the landscape, really be an authentic response to these larger moves, to this larger place, and also help check all of those other boxes that we're trying to achieve for the project. And so that's kind of what we're going to walk through right now, just kind of step by step. And this is sort of how our process works, really thinking through all of the different moves we make and making sure that they're meaningful in some way. So you start with the traditional campus building. This is suggesting it's OSU. It's a brick building, very simple form. And then move it to the OSU Cascades campus, and you move it to that high desert landscape. Part of the language, the architectural language that's been established in the buildings that have already been built for this campus is the use of wood. There's wood on all of the exteriors of the different projects that have been built there. And so we started that just as a base. You know, let's say we switch from that, the brick vernacular to the wood vernacular. And then we see that landscape drop off. We see it transition down to the bowl. And what is that kind of open and kind of fluid, transparent ground plane that you saw on the flat site then cascades down with the site as it moves into the bowl. And then the same thing happens with the program. The stack of the building begins to step down as well. And so it really is happening because of the moves that we're making, or the moves that have already made in that landscape. The next big move is to divide the form, break it down the center. And there's a few reasons for this. One is that it creates these framed views to the west, so you can capture that beautiful view of the Rockies, or of the Cascades, that really defines Bend and the high desert in a lot of ways. It's looking off to the west and seeing that mountain range. And then from there, we also looked at creating then, by splitting it down the middle, 2 uniform bays on either side. And this really, we felt, was the best way to think about flexibility for the future. Because if we could figure out an optimal bay depth that would work for a number of different program types, and then just modulate the length of those programs and understand kind of what the sweet spot is in terms of the layouts of those spaces, you could really have a lot of flexibility in terms of how these buildings change or are organized internally, both initially and over time. So you can imagine where different scenarios where the classrooms are grouped and the labs are grouped, or maybe, as you can see before, they're distributed in even ways and mirrored about the center corridor, or maybe they just end up being wherever they need to be for functionality or sustainability purposes. But we really wanted to just create a sort of open framework around which we could think about the building organizing in a number of different ways, and it could change over time. It's also optimized for mass timber. For anyone who's done a mass timber project, you know the challenge of running utilities in a mass timber job, mostly because of these deep beams that you end up getting on these larger spans. And so if you can have a shorter span down the center that allows you to run all of those utilities that can then distribute into the spaces, that's a huge advantage. And so we were really thinking through that lens when we kind of divided it down the center. We also were really curious, as you can see in this image, about how we could space the columns close enough so that we could eliminate any perimeter beams on the building. And that was really due to some of the sustainability goals that we had. We wanted to optimize those spaces for daylight and views. And so by limiting the depth of the bay and also eliminating the perimeter beam, we were able to get these tall apertures all the way up to the underside of the structural deck for that deep daylight penetration and those high views out to the sky. The next move is on the north side. We broke it down the middle, and this really has to do with the place in which we're building. It is a way for us to open up to that future plaza and open up to that future campus, especially at this kind of critical moment where people are entering this new campus and descending down into that campus bowl. It also allowed us to think about then the south side as the more of the workhorse side of the building, really thinking about it as a service spine, a place to consolidate some of these more rigid functions like circulation, like mechanical systems, like bathrooms, cores, things like that, and then also service access off of the road. So that means that this back spine is really sort of rigid in some ways, but it also means that the campus side, on the bowl side, has a lot more flexibility in terms of how it develops for future projects. So this is sort of envisioning taking the AB2 prototype and marching it along the edge of that large promise mine and thinking about how the north side might change and modulate based on unique conditions that happen as the campus grows and changes. And finally, we complete the form. We look at the roof form and then articulating the north and the south facades, north and south facades in a different way than the rest of the building. This allows us to sort of limit the amount of wood that we use for durability and long-term maintenance purposes. It allows us to then protect that wood. And it also allows us to think about some other factors such as weather protection. As you can see here, the deep overhangs are really important in the winter in terms of creating walkable paths that are protected from the snow. And it also allowed us to maximize the on-site energy generation to help us hit those net zero energy target numbers. And then finally, it allowed us to think about those north and south orientations that really are intended conceptually to be mirrored to the opposite side of the bowl when that side of the campus gets developed, to tune to orientation and to really think about controlling how we are getting the peak cooling modes into those spaces to really keep all of our options open in terms of our mechanical strategies for the building, which you'll see is tied to the embodied carbon story of this project. And so all of those different moves in concert kind of led to the building that you see in these renderings here. We're happy to say that this is all going to be there in real life next year, towards the end of next year. We broke ground a couple weeks ago, so we're excited to have this thing up and running. But hopefully, you know, that's kind of an insight into all of the different moves that we've made and tried to run each of those decisions through a sort of lens of what is it doing for the building, what is it doing for the site, what is it doing for the owner and the user. So from there, we're going to jump into our discussion about some of the decarbonization strategies now that we've seen how the building form kind of came to be what it is. The first one we're going to talk about is mass timber. I'm not going to run through all of the myriad benefits of mass timber or potential benefits because I think anyone who is practicing architecture in the Pacific Northwest is very familiar with these. But the one I will talk about, or one of the ones that I will talk about, is the sourcing of our wood. So we are proud to say that all of the structural wood for this project is being sourced out of the Pacific Northwest. Our glulam columns and beams are being sourced out of Eugene, and our CLT panels are being sourced out of Colville, Washington. And we're particularly excited about the CLT panels because we are getting them from Boggin Timber, who is a member of the Northeast Washington Forest Coalition. And their mission really is to improve the ecological function and fire resilience of our national forests. And it's a really unique partnership between a number of sustainable nonprofits and conservation nonprofits and you know, industry leaders as well. And this is just kind of to highlight the fact that just using wood isn't really enough. We need to make sure that through the carbon lens, we're trying to make an impact. We're getting that wood from the right places through, you know, through sustainably managed forests. Folks are really thinking about not just using wood, but also making sure it's coming from the right place. And why that matters is right here. What we're seeing is a sort of a graph that folks who are in sustainability circles are probably familiar with. But as we start to understand more and more the urgency of action around climate change, the timeline gets shorter. And so instead of thinking about building operations over the next 80 years, if we don't do something now, it's really a 30-year timeline that we need to look at. And when we shorten the timeline, we suddenly see that the proportional impact of embodied carbon, that's the energy that goes into actually making all the materials and transporting them to the site and constructing them, has compared to the operational carbon, it's almost a 1-to-1. And so that's sort of something that we're going to start talking about a little more now, because we feel like we've really kind of zeroed in on operational carbon over the last decade or two, but embodied carbon is sort of a new frontier, and frankly, we're still trying to get better at it. But here's some few things that we did. It's not just about what materials you choose to use for sustainability reasons, but it's also how much material you use. And so if you can minimize the use of material, that's also an interesting strategy to reduce your embodied carbon on your projects. And so related to mass timber, what you're seeing here is a study. This is a 40-foot long panel, which is a typical size for a CLT panel. And looking at 2 different column spacings, which seems like a pretty simple exercise, but like I said before, we're trying to eliminate this perimeter beam and really utilize the ability of the CLT to span on its own. But by creating a 10-foot column spacing as opposed to a 13 4-foot column spacing that allows us to go from a 5-ply panel down to a 3-ply panel, which doesn't seem like much. And intuitively, you might look at this and say, well, there's more columns and beams, so there's more material. But because there's so much more floor area, that actually reduced the overall structural material in the project by 30%. We're estimating. We haven't done the hard numbers on it yet, but I've been working with my coolers over at Katina to really crunch those numbers. So small moves like that can make a big difference in terms of the weight of our buildings. It's less concrete, it's less foundations, and it's less wood fiber. We're also trying to get smarter about concrete. We are looking at collaborating with our structural engineers and our concrete suppliers to really lengthen the cure times on our concrete slabs and on our concrete walls, our foundation walls, and on our cores, because it's going to allow us to then reduce the global warming potential there. Admittedly, we did not get out far enough ahead of this on this project because this is actually fairly new information to us, at least. But this is something that we should all be trying to do on the projects that we have moving forward. And so up to this point, we've primarily focused the conversation around structure because it is the biggest piece of the pie. But from here, we're going to kind of pivot to mechanical systems and enclosure, because as you can see, those are the next largest. This is for a high-rise building, but it really translates to most scales in terms of the scale of impact of that embodied energy. And so in terms of the mechanical systems, we're going to talk a little bit about refrigerants, because for most folks who are probably working on budget challenge projects right now, VRF comes up a lot. That's variable refrigerant flow. And that's because it really is the cheapest system out there that helps us achieve the operational energy goals that we have. But when you look at VRF through the lens of embodied energy, it's problematic in a lot of ways. Because if you look at this graph, the refrigerant in our systems can create up to a third of what we're talking about in terms of the embodied energy or the global warming potential of our mechanical systems. And that impact just grows over time. But the challenge we have with mass timber, and I think you see this a lot, is we have this impulse to expose the wood. And so that's a great impulse for the interior of the space. But if that means you also want to have folks from the outside look in and see it, it kind of leads to this impulse to overglaze our buildings. And so we really wanted to make sure that we were thinking about the envelope through the lens of keeping as many options on the table in terms of our mechanical strategies to move away from refrigerants and find other mechanical solutions that were viable but based in hydronic systems as opposed to refrigerants. And so this brings us back to the facade and the expression of the facade, and the decision we made to create those north and south sides in a different way and articulate them in a different way. In terms of the inspiration for some of the patterning and materiality, we really looked at the mine itself. There's these really incredible deposits of pumice that have this really vivid, kind of beautiful striation and this wonderful tone of colors. And so we're really trying to see how can we kind of mimic some of that light and shadow, how can we mimic some of those tones in the way that we compose a facade. And we also were trying to keep it economical and keep it simple. And so we really tried, we found and we looked around for what the right material might be, and we found this really kind of modest material. It's this metal siding that's this corrugated form, but we also really liked it because of the depth of that corrugation. You're getting a 4.5-inch depth, so you get this really deep shadow across these surfaces. And in addition to that, you also get shading from it, and that's what we were trying to push. Is there a way to think about the facade not just as an architectural expression, but as an energy strategy that isn't an applied energy strategy? It isn't something that you're attacking onto your building, but really it's baked into the wall assembly. And so what you're seeing here is the 4.5-inch deep profile, and then we took the rain screen clip and just pushed it out further than it needed to be. It creates more of an air cavity, but that's kind of free space in a lot of ways other than the returns of the sheet metal. But that move unto itself created a full foot of shading in the vertical direction on these kind of vertically oriented apertures back to the glazing surface. And then by breaking up the elevation horizontally, we were able to then get an additional 16 inches of depth in the horizontal direction of this horizontal shading. And we were also then able to break up the material to a scale and a size that was compatible with the product that we were looking at. And so this is looking just at that one bay, a 30-foot bay with 3 10-foot column spaces. And from here is where we really started to plug Lyle into the process, and we started to do some real explorations of what is the relationship between how we develop this facade and how we can help mitigate the embodied carbon impact of our mechanical system and really hit those net zero targets. And so I'll pass it over to you, Lyle, and you can talk a little bit about the Target Finder tool that you developed over at AEI.
Sure. So, really early on in concepts and at the start of schematic design, we were prototyping these facades as well and trying to determine what major moves we would need to take to really set us up for success on the project. And we really analyzed the facade performance within these different key performance indicators you're seeing on the screen. And we wanted to consider all of these metrics to make sure we were balancing them and optimizing them to kind of maximize the objectives as best as we could. So those KPIs were aesthetic vision, trying to preserve the views to the outdoors, as well as expose that beautiful timber ceiling from the outside. Obviously, annual energy consumption was a key objective, trying to get to the net zero energy target. And sort of coupled with that was looking at the peak cooling loads and how that impacted the HVAC system selection. So we had a real careful eye on trying to minimize the cooling loads through the facade so that we could unlock more efficient HVAC technologies. And we're really trying to utilize either radiant heating and cooling systems or hydronic-based sensible fan power boxes, and really unlock that potential again by minimizing the cooling loads to use those high-efficiency HVAC systems. Daylighting and cost, additionally, were metrics that we considered. What you're seeing at the bottom is an example of a tool I'm going to bring up and demo real quick. Share my screen. Wrong screen. There we are.
Oop, lost it.
All right. So analysis really impacts design through the use of effective communication and visualization tools that allow stakeholders to understand the relationships and really make decisions with confidence. So what you're seeing on the screen here is a target selection tool, and it's some of this parametric analysis we did early in design to understand the impact of these facade concepts on different outputs. So on the left-hand side, you can see we looked at space type, orientation, window to wall ratio, as well as fin spacing and depth. And we did a bunch of parametric runs to understand how that impacted the peak cooling loads, lighting, heating, and cooling energy, as well as spatial daylight autonomy. So just to give an example of how this works, let's say we looked at an office space on the south facade. We had 40% window to wall ratio, 1 foot space fins at 12 inches of depth. You can take a peek at that run, see that you have a peak cooling load of 3.79 watts per square foot, and understand some of the metrics there. Maybe you want to look at the impact of multiple fin spacing. So looking at 1, 2, and 3 foot spaced fins, you can see the range of peak cooling load between 3.7 and 5.3, and also understand the impacts of lighting, spatial daylight, and all the other metrics. What's really compelling though about this is you can kind of work it right to left and optimize for different outcomes and see what design metrics and design moves are on that critical path. So just as an example, let's say we want to target good spatial daylighting autonomy, maybe 55% or above. We'll look at the office on the south again. And so even just looking at better spatial daylight, you can see a 1 foot fin spacing does not agree with that type of result. So that shows you that's off the table. We also talked about kind of minimizing those peak cooling loads as well and trying to bring those numbers down as much as possible to unlock those more efficient HVAC strategies we were looking at. So trying to maximize spatial daylighting and minimize the peak cooling load led us to this combination of design solutions. And let's say we picked the 35% window to wall ratio to maximize the aesthetic vision. That shows us that approximately 2 foot space fins and about a 16-inch fin depth was appropriate for that. So, this is again a visualization and decision-making tool that allowed the integrated project team to sort of understand the relationships of many metrics at once. And you can really kind of design at the speed of conversation and build the bundle up in real time and kind of play those what if scenarios to really drive the design and maximize the outcome.
Awesome.
I'll toss it back over to you, Scott.
Fantastic. Thanks, Lyle. And so looking at it through that lens, as you can see here, folks see on my screen?
Yep.
Awesome. Perfect. And so we really took that single bay and we wanted to understand through that single bay, thinking about in these 10-foot bay increments, or the 10-foot column spacing, what does it look like as we sort of increase the amount of glazing we have by these 6-inch increments, which is the module of this corrugated panel that we had chosen as sort of facade expression. And so as you can see at 31%, all the options are on the table. You have the best energy performance systems on the market, and you also have the VRF and the VAV, and the green indicates the operational energy potential in a good direction, and then the red indicates the global warming potential in a negative direction. And so from the 31%, you know, everything's there. 35%, that's taking 6 inches out of each 10-foot portion of the facade. We've already lost radiant panels as an option. And then if you take it one step further and take it another 6 inches, we suddenly have painted ourselves into a corner in terms of our system selections. And so these sensitivity studies really helped guide some of the decision making around the facade and making sure that we were doing the right thing from both an energy and a carbon perspective. And we landed on that 35% glazing expression for the building. And that's what you're seeing here. One thing to note is these larger expanses of glass are north facing, and so we don't have the same peak cooling load issues. And on the opposite side, we actually have a solid to offset this void. That's our building core. And then as you move to the inside of this space, this is, you know, where we start to get excited about some of these synergies, because as you can see, we're getting that deep daylight, we're getting those wonderful views out to the sky, but we're also seeing a mechanical system in this image, which is hard to spot, but all the heating and cooling is being managed in this perimeter zone at the base of the wall. And so we couldn't really afford a raised floor on this project, and it actually didn't work from a program perspective either, because a lot of these higher education projects have very particular vibration criteria that just aren't compatible with the raised floor system. But we still found a way to both get a hydronic system in place, have it be at a competitive price point relative to VRF, and also keep it off the ceiling plane so we could really expose that beautiful CLT structure. And from here, I'm going to pass it back to Lyle, who's going to talk a little bit about what this system is, these hydronic fan-powered boxes, and then talk about how all of these moves kind of get us further down the road towards our net zero energy target goals.
So we really wanted to, you know, select an HVAC system that was optimized for our net zero energy target, for the aesthetic vision of the project, as well as first cost. So we ended up with a real balance of those and went with what's called a sensible fan power box. So this is a hot water and chilled water heating and cooling type of unit. And there's small little fans in there that are highly efficient. Think about the size of a computer fan stacked up into an array. But these provide all the heating and cooling needs for the zone. We had a dedicated outdoor air system that was supplying tempered primary air to the space, but really these units, by keeping the cooling loads low enough that we could fit them in only along the perimeter wall, really provides an energy efficient system that's a step above the traditional VRF or a VAV type of system. It's also really cost competitive as compared to a radiant heated and cooled ceiling or a full chill beam solution with almost about the same amount of energy performance as those types of systems. So we found a good balance of cost and energy efficiency in that well. So again, you can see on the interior rendering here, we really wanted to, one, keep the ceilings open and really have that beautiful mass timber ceiling exposed. So that was a main strategy that kind of informed the HVAC distribution. On the lower left-hand corner here, you can see all the primary air, as well as the hydronic heating and cooling for the building, was routed down the service. And there's no air that goes into the space via ducts. By keeping that bay to about a 30-foot depth, we're able to just have terminals along the inlets here that could throw the ventilation air and really remove that need for ducts to run through the space to provide ventilation. Another move we made on the top left here was we had a 6-way valves located in the corridor, and that allowed us to only run 2 pipes instead of 4 pipes of water down along to get to the perimeter to those sensible fan power boxes. And those 2 pipes were hidden along kind of deep columns and beams and within these little wall cavities that were created. So you really don't see a lot of the distribution here. And so this sensible fan power box coupled with a dedicated outdoor system was really a great way to balance the aesthetic vision, keep it cost competitive, as well as maximize the energy efficiency on that path to net zero energy. You can kind of see another beautiful rendering of it here as well. And just again, kind of keeping those cooling loads low enough so that we could have these smaller units located along the wall here and not have to put any units interior to provide additional capacity was part of that initial facade and load study. So those were sort of some of the early concepts that informed the prototyping of the massing as well as the facade. And not only did OSU want the building form to be prototype for the future, but they wanted the energy design and the systems design and the path to net zero to sort of be a prototype for the future buildings on campus as well to achieve a high level of energy efficiency and a high level of building performance. I'm going to kind of talk a little bit more about the net zero energy design process that we went through. So getting to zero on this project, Scott and I haven't really talked too much about the program, but this isn't your typical classroom and office type of university building. There's actually a mix of labs and really interesting program here. There's a biomechanics and kinesiology lab. There's actually a cadaver lab that requires 20 air changes. There's a maker space and a machine shop, spaces that both have intense equipment requirements as well as specialty exhaust systems. So, you know, the research and teaching lab component of this, those have pretty high EUIs, energy use intensities to begin with. So sort of this typical EUI was around 80, and trying to get to the net zero EUI, we were looking at trying to get down to about 28 EUI overall. This project is participating in the Energy Trust of Oregon Path to Net Zero project. Sort of the industry standard from the existing building stock would have put this building around 140 EUI, and trying to get down to the 80% savings target for the AIA 2030 challenge would put the EUI down to 28.6. What's interesting is getting to this EUI could actually include the impact of renewables if we wanted to, but sort of serendipitously enough, we found out that the amount of renewable energy that could be produced on the roof area of this building fell sort of in the 26 to 29 EUI range. So trying to really hit OSU Cascade's goal of creating net zero energy for this project, we're trying to have the building consume about 28 EUI on its own. So again, in spirit of the in-process lecture, we're trying to talk a little bit about the approach to net zero energy design here. And we really start at the top, and it starts by reducing the demand for heating and cooling energy and reducing the demand for lighting, and applying passive systems as much as possible to reduce that demand for energy. From there, you look at applying the most efficient active mechanical systems that you can, and really try to minimize the cost and space required for renewable energy to offset that building EUI to hit the net zero energy target. So sort of a code compliant building would be around 80 EUI. Applying some of those demand reduction and those passive strategies that we talked about earlier got us down to about a 65 EUI range. The careful attention to glazing and shading. We also went with fiberglass windows on a majority of this project. And, you know, going with the fiberglass frame windows allowed us to get almost triple pane levels of glass, but still at a very lightweight and very thermally efficient type of construction. We have all LED lighting design, full daylighting controls. Equipment power was another area we really attacked and looked at some controlled receptacles, particularly in the machine shop and maker space, to help keep those internal process loads down. So kind of the next step in that net zero energy design was applying the most efficient active systems that we could. Sort of talked earlier about the zone level heating and cooling systems and the dedicated outdoor air system for ventilation, but I want to briefly touch on the plant system, and I'll get to that in just a second. One thing to note again is that if we would have applied these types of solutions to maybe your more typical open office or your more standard classroom building, we probably would have been down in the range of 25 EUI and probably able to hit that net zero energy target. But with this program, we were closer to 37 EUI, and we really needed to push hard to try to get to that more aggressive level of performance for this type of mixed lab and classroom building. So getting back to the active systems, a key component to producing the heating and cooling as efficiently as possible was going with an open loop geo-exchange system on campus. So the open loop means we actually pull the groundwater out, send it through a heat exchanger to exchange heating and cooling energy with it, and then inject that water back into the ground on another source on campus. Not only did this allow us to get really high performing levels of heating and cooling efficiency, but it really supported the decarbonization goals and the long-term electrification goals that are kind of inherent to the operational carbon conversation. So this is a 100% electric heating and cooling building. There's actually no fossil fuels that will be used for combustion heating at all, and there's actually not even a natural gas line to the building. So a 100% electric, highly efficient heating and cooling plant. Another thing we wanted to talk about is operational energy conservation and the opportunities that provided. So we sort of at the end of SD got to about a 37 EUI, and we really wanted to engage the owner and be transparent about our assumptions. They really carefully worked with us and actually gave us some feedback about the use of the building. They wanted some more weekend events in the flex lobbies, some more occupied hours in the cadaver lab. And so that actually bumped our EUI up a little bit. But it was really important to be transparent and get them on board. We also looked at the impact of operations as an opportunity for them to reduce energy much further at maybe sort of a low cost type of strategy. So we looked at really enhanced temperature and ventilation setbacks, and through these lists of operational ECMs, we were able to get the EUI down to 31. And again, I think it's just really key that we were open and transparent with the owner about this. They understand sort of this is the part of getting to net zero that's on them, and they have to be diligent and aggressive about operating the building to get there. But presenting them as opportunities and working with them really allowed us to kind of find some more energy savings on this project. So we were at about 31 EUI and just starting the DD design phase. And this is the part of the phase, the project where, you know, we really have all our silver bullets in the project. We've got all the big strategies, but really trying to push that extra 3 or 4 or 5 EUI starts to hit some diminishing returns, and even more importantly, starts to become a lot more costly. So we did some parametric energy and cost analysis throughout DDs. I don't really want to focus too much on the specific concepts, but we looked at sort of the first cost to EUI savings, and this is kind of the best bang for the buck of the strategies we looked at. So trying to apply these in sequence would determine the most first cost efficient path to our goals. We also kind of looked at the overall magnitude of those EUI savings to see, you know, is this really going to move the needle more or a lot? And that helped us to kind of focus in on some of the strategies as well. Here again, we use the target selection tool to try to optimize and bundle, and this really looked at the interactive effects of all of those options and provided a much more accurate representation of if we bundled different groups of strategies, what the cost and energy impacts would be, and help to kind of identify the critical path. So this was our recommended bundle, and we're able to get down to that 28 EUI range for only about $120,000 of additional cost at DD. As you can see, as you start to apply these, the additional cost to kind of squeeze out little incremental EUIs becomes really costly. So this was a strategic approach we had to work with the owner to really get those last few EUI savings and achieve our targets. So the DDE-ECM bundle put us really within the range of the net zero energy target production. And from there, we set the project up for success. We had all these concepts baked into the cost model, and really just kind of we're writing things out from there on out on the energy performance goals. So I'm going to talk back to Scott now. He's going to talk a little bit about the interiors and the expression there.
Awesome. Thanks a lot, Lyle. That's great. And so from here, we're going to kind of jump back to the interiors and really just circle back to the building as a whole. As you can see, we really went through an arduous process to keep this building simple, to have all of the big moves almost be hidden to a certain extent. So when you look at the building, you just see the beauty of the architecture and the beauty of the structural system. And so from there, how can we have an approach to our interior public spaces that really takes that same sort of approach? How simple can we have it and still have it work and be beautiful and work well? In terms of the interior palette, the one sort of material that isn't wood other than concrete that we're introducing into the interior structure is these beautiful steel connections that are black steel that would allow the glulam columns and beams to come together at these seats. And so those seats would be exposed to the underside. And so we just took that as a cue to develop a series of signage and screens and guardrails that pick up on that language. And so this is a work of our interiors lead on this project, Emily Wright, totally slam dunk this whole thing. And what you're seeing now is our signage solution in terms of wayfinding down the corridors. One of the challenges in these mass timber structures when you have this tight column spacing is that it can get a little bit disorienting because you're just kind of seeing this sea of columns as you look down the corridors. You can't really see the walls between them. And so we just looked at this really simple column wrap that's made out of that stained steel language with a subtle profile that matches the view that really inspired that initial break down the center of the building. And then as you move to the large space that leads out into the landscape, we looked at a really simple language of a steel guardrail with a metal mesh, and then introducing that same language into that large cascading grand stair that again creates that strong connection to that carved landscape that we're using to transition down to the bowl. And so hopefully that is a good synopsis of our attitude and our process about design. You know, we really want to create beautiful, coherent buildings, but also buildings that are informed by sort of rigorous research, performance-based analysis, in addition to all of the other functional and, you know, aesthetic considerations that we have on other projects. But at the end of the day, you know, we just want folks to feel like this building is making an impact, is a positive part of their community, and is really contributing to their everyday experience when they go to school at OSU Cascades. So from there, I think we'll just open up to questions.
Yeah, thank you guys. Thank you, Scott and Lyle. That was a fantastic presentation. At this point, we are going to take questions from the audience. So feel free to turn on your cameras or use your raise hand function if you've been able to figure out where that is with the Zoom functionality. If you want to do that, I'll call on you, or if we can't figure out how to do that, just unmute yourself and ask a question, and we'll see how things go. I didn't see any questions in the chat box yet, so you can also type a question into the chat box if you like. All right, well, while we're waiting for you guys, oh, here's a question. Okay, so I have a question for you guys. I am curious, how much of a linear process was this design? The diagrams and the process that you outlined looked incredibly linear in a really good way. And so I'm curious, did you guys start collaborating on these generative studies early on and have them sort of inform the project throughout the process? Or, you know, when did you really start collaborating on some of those window and depth and sort of analysis studies that you guys were showing?
Yeah, so we actually got this project through a design competition. And so a lot of the really messy stuff in terms of leading up to the sort of clear concept that we landed on happened during the lead up to the design that we presented as a part of that competition. But believe it or not, the Target Finder tool that you saw, where we're really analyzing the facade, we showed that in the interview. Like, we, from day one, really were thinking about this project being an integrated process with our energy modelers, with our engineers. So, you know, and that's kind of, I think, what it takes if we're going to really kind of stick the landing on some of this stuff, is really having it as a part of our process as early as possible.
Excellent. Okay. Scott, I'm going to ask you to stop sharing your screen if possible.
Yeah, absolutely.
And so we can see anybody's cameras who wants to brave to show your face. And in the meantime, we've gotten some questions in the chat box here. So some quick ones. What's the LEED certification target for this building? Lyle, do you want to answer that?
So the project is not pursuing LEED certification, but we are achieving a minimum LEED Silver or equivalent to the OSU Cascades requirement. So we're kind of keeping a scorecard alongside, and OSUC's requirement is LEED Silver equivalent, but we're not actually applying for certification here. They are really focused on the campus goals of net zero energy and net zero water.
Great. We've got another question for Lyle. Could you explain a little bit more about the parametric process that generated the iterative line diagram?
Sure. So, you know, we were working real early with Scott and the other designers at SRG. They were sharing kind of Rhino and SketchUp models with us. So we were taking the form and expression and using that to create our massing. We used Energy Plus and Open Studio, and we did parametric energy analysis with Energy Plus and Open Studio, as well as the Radiance plugin for the daylight metrics. And then we kind of pull all those results out. And the visualization tool was an in-house tool developed by AEI, but the type of plot you're seeing is called a parallel coordinates plot. And so being able to put in that parametric data set and explore it in a parallel coordinates plot was sort of the workflow that we took for the parametric analysis.
That's great. Here, I'm just going to start reading a few more of these questions. Maybe I'll throw this one to you, Scott. Can you talk about some of the strategies that were specific for this project to the high desert climate?
Yeah, definitely. I think the high desert climate is actually more manageable than some other climates in terms of diurnal temperature swings, in terms of those peak cooling loads that you're dealing with in Bend. And if you are looking sort of in depth at what is kind of triggering our use of different types of mechanical systems, even though the heating loads as a percentage of the total energy use is higher, the system's decision making is usually determined by the peak cooling loads and what kind of capacity we have to keep those spaces cool when you have those large solar heat gains into those spaces. And so that kind of led us down the road in terms of the climactic response of the architecture that was distinct to the high desert environment. I'd say the other piece is just the connection to the landscape, finding ways to really kind of embrace this beautiful place where we're able to build.
Excellent. Okay, I think Jacob Peel's question was answered. Lyle, you sort of went over the different programs that you used. Do you want to just repeat those so we can get that for our listener here? What specific programs did you use for that actual tool that you demoed? What's that called?
So again, the whole workflow was we got SketchUp geometry models from SRG, and using the Open Studio plugin, we're able to use Energy Plus and the Open Studio parametric analysis tool combined with Radiance to get all the energy simulations, the load calculations, and the daylighting runs. From there, we organize the data, and the tool, again, is an in-house AEI developed tool, but it's a parallel coordinate style plot, and our AEI tool basically just puts a little bit of structure over it so you can compare options side by side, kind of get that tabular view of options below. And this really allows us to just kind of manage different projects and different levels of analysis so that we can share them with clients.
Can I follow up on all that?
Yeah, absolutely.
Sure.
Oh, yeah, I guess it looks like a lot of tools that I've seen already before, you know, and I guess I'm sort of wondering how it feathers together. You mentioned that it plugs into SketchUp, and that is interesting.
Mhm.
I don't know if you have anything to say about that, but the other things was the AEI tool, the parallel plot. I wonder how hard it is to pull in and out of those sorts of analysis, because that's really a brute force database that you're creating, where you're running every analysis instead of just running the ones that matter. And I wonder, I guess, yeah, like sort of the, how did Scott say, like, hey, can we look at this? And then you say, yeah, I'll get back to you in 2 weeks, 3 weeks, or?
Right.
No, I mean, it was identifying, you know, what are the different inputs we want to test and what are the ranges of those, or what do we expect those might be in the real design? So, you know, what's
Maybe, I guess, how did you develop those values?
Well, yeah, I think it kind of started just from understanding best practices for a net zero academic building, and then testing them, and not just resting on our laurels and saying, okay, this should work, but really vetting them in a robust way. And I think that's what allowed us to get where we got. And I think it's also understanding, you know, where you sort of reach a tipping point in terms of your system selection, things like that. A lot of times, I really feel for our energy modelers, they're just kind of taking what we throw at them and figuring out a way to make it work. And it's not a dialogue. And so really having that back and forth and saying, oh, okay, this is a step too far. Well, let's dial it back a little bit. That's the kind of feedback that we need to have with our engineers to make sure that we're really tuning our buildings to be as high performance as they can be without sacrificing the sort of experience of the architecture.
I completely agree. Yeah, I wish they were like co-collaborators in the office every day so that you could have the rapid sort of like collaboration. But
yeah, and have it be iterative. I think that's a really important piece of it. Not just like run an energy model and bake it and hand it over, but have it be a design tool and not just a sort of confirmation tool.
Yeah. So was this something that went back and forth for months, you know, as you guys honed this design? Was it just kind of a continual tool that you used?
Something we used throughout. I mean, we looked, you know, this was kind of the single zone envelope prototyping. Again, I mentioned later, we looked at a whole range of whole building ECMs. We also looked at sort of water efficient design. And so really this tool, you can put any results of a parametric analysis into it. And that could come from a computational program, or it could just be spreadsheet calc. So it's really just a visualization and decision-making tool. And as Scott said, you know, kind of applying best practices to create the range and values of these things was where we started. But it gets really interesting when you try to kind of optimize for multiple outcomes. You know, like we wanted to maximize the daylighting, but minimize the cooling load, sort of see what set of strategies would lead us there. And that's the real power of kind of a visualization tool here. But I don't know, Jacob, you know, you can feel free to reach out to me. Do you work in computational design or with these type of workflows?
I would love to reach out to you. Yes. Yeah. So I've got your name written down already. I can.
Jacob, I can send you his contact info.
Oh, that's great. Yeah. Thank you. Thank you.
Yeah,
Ben.
you bet.
I wondered how networking would happen in this virtual, you know, world now that we all.
Here it is.
Yeah, we're trying.
Exchanging virtual cards.
So really talking about it up front, like what's the possibility space, and then running those parametrics of all the computations over a few days. Then we can really come back again and play the what ifs, build up the bundle in real time. And it's not like, oh, what happened? You know, I really like A, B, and C bundle, but I want B with this one little thing switched out. You know,
Yeah.
Then I have to rerun everything later. It's sort of generating the data set before, and these types of tools let you kind of get the answer, build the bundle, and play what if sort of
Yeah.
at the speed of conversation. So you don't have to come back two weeks later, for example.
Right.
Okay, this is fantastic. I'm going to switch gears a little bit and take a question about cost analysis. This is, I think, an interesting and very applicable part of the process. So maybe, Scott, you could talk a little bit about who did cost estimating during the design. Was it a consultant, or did you have a pre-con services from the GC? And just kind of describe that process.
Yeah, so this project was CMGC, which was great because it brought Swinnerton onto the team early, and they were able to do some of this iterative estimating that allowed us to kind of drive towards the target values that we were trying to achieve on the project. But actually, for some of the envelope analysis, we also reached out to a third party because we did set aside a little bit of the budget that was just exclusively to help us drive towards these net zero targets. And so some of that bucket went to someone who is, John Bales, was able to help us break down some of the associated costs with some of the ECM strategies that you saw related to the envelope. And then some of the more systems related costing was done by Swinnerton.
I think having that parallel cost estimating, particularly in schematic and early DDs, where sort of SRG's third-party cost estimator and John Bales was working in tandem and sharing information and assumptions with Swinnerton as the GC. Personally, I feel like that parallel cost estimating in these types of integrated project deliveries and really kind of helps the cost model be real and be as effectively used as it can early on, and kind of keep both sides as honest as possible to hit the cost metrics.
That's great. Okay, we have more questions in the chat box, but I also want to let anyone know if they want to unmute themselves and ask a question, feel free.
Back to chat.
Okay, all right. Well, here's another one. So this is from Kurt Wilson. How are you predicting climate change in the long term? So presumably as the climate gets hotter, are you factoring those types of things into the whole lifespan of this building, like in the next 20, 30 years? Are you taking those types of climate change configurations into account for any of your analysis?
Yeah, that wasn't a primary driver for OSU on this project, but we do look at long-term future weather files. We can run different combinations of them to see the impact. Also looking at different design day conditions in the future and how that might impact the load or the size or the cost of the mechanical systems. So we did look at those and use some future weather files and the energy and loads analysis. But OSU was really kind of focused on sort of the initial performance more so than making big decisions about what might happen in 20 or 30 or 50 years.
Mm-hmm. Okay, I've got another question for you, Scott. How does this project and this process compare to the other work that you've done at SRG in the past and kind of the other current projects going on at SRG?
Yeah, I mean, for me personally, it's been a process where each project I've worked on before has really allowed my knowledge base and the team's knowledge base to build from project to project. So, for example, the Sensible Fan Power boxes that we're using on this job, PAE introduced that on my previous job, which was the 4th Montgomery building, and really understanding how we can manage our blazing areas and get the right wall assemblies in place to really optimize how we use those systems was kind of a breakthrough for me personally. I'm like, oh wow, there's something else that's not a chilled beam or a VRF or a VAV that might give us a path forward in terms of hydronic systems on a budget. And I would say just big picture strategies too in terms of how can we take a concept, bring that clarity of that concept through, but also have it be something that's responsive to some of these more external demands that we have around embodied carbon and around energy performance. And I would say that that's a thread through all of our projects. They vary widely depending upon project type, but I'd say the same rigor of investigation goes into each one. Although it's you know, a softball stadium is very different than a courthouse, so I can't tell you that those two really translate very easily, other than we want it to be a beautiful structure.
Yeah. It seems like you and Lyle worked really well together on this project, and it's been awesome to hear how you guys collaborated. Anyone else have any other questions from the audience? Feel free to unmute yourself and ask. Our presenters are more than willing to answer.
Well, I'll ask, and I don't have the hands feature as a host. So Scott, I'm curious. What we kind of heard tonight is the emphasis on net zero design strategies, and you really reinforced the importance of the design approach to create a really clear, clean, simple building. And I'm curious if you found were there conflicts between those two that really required good coordination with the design team and the client to understand the priorities? Did you find that if there was something, for instance, that was wasn't as clean and clear, like exposing structures would have allowed to get quicker to lower EUIs? What were those strategies, and what were the areas that kind of surprised you in this process?
I'm trying to wrap my head around the question a little bit.
Were they in conflict at all?
Oh,
were those two strategies in conflict? And that were there some things that, had you not had such an emphasis and a rigor on a clean building, you could have maybe found other net zero strategies would have been more available to you?
Probably, yeah. But I think that's kind of what we're trying to do at SRG is do both. Can we thread the needle? Can we create something that doesn't look like the kitchen sink from a sustainability perspective in terms of sort of added functions, sort of something that's additive, but really something that's more reductive, that's getting back to just the purity of the systems, the purity of the building, and a really simple tectonic clarity that does both. I think it's sort of a yes and. Because yeah, there are always, you know, more things you can do, and that was kind of a little bit of what we were looking at in those ECM strategies, those energy conservation measures that Lyle showed. One of those was creating a deeper horizontal shape. It's taking that frame and pulling it out even further. I was not a fan of what that did architecturally, but we wanted to see, did that move the needle in terms of performance? And the reality was the enclosure was robust enough as it was, and was providing enough shading as it was, that it barely moved the needle relative to the added cost of what that would have done. And so those are some of the moves that we tried that were still, you know, kind of working architecturally, but not as nice. But we tested them anyway, just so we knew.
Yeah, one of the early attempts to keep the clean interiors was the thought of, what if we run that hydronic piping in the slab? But that would have actually caused us to increase the slab depth by a couple inches, adding a lot of cost and concrete and cement carbon, embodied carbon, to the project. So we had to kind of pivot away from that and look to the ceiling solution. And there was a little bit of conflict with trying to put all those six-way valves out into the corridor as well. That was a little bit of a cost item that kind of came up in the project, and we had to sort of compensate for that additional cost of all those six-way valves. But you know, we found other areas, and we didn't want to compromise on that clean vision and the energy performance. So, you know, we had to find some other areas to compromise and recoup a little bit of that cost later on.
And to be honest, it was a huge struggle to keep it as clean as it is, as you see in those images. Some of those images are exaggerated a little bit, but because they're sort of older. But you know, huge credit to, you know, David Webb and Jenna and Lisa on our team, who really did a deep dive into that the level of coordination it takes to kind of pull this off in a mass timber structure.
And actually getting all those utilities to fit is a bit of a rat's nest. And so that was an internal MEP design challenge. to get it all fit up in that central corridor while keeping access. We were trying to kind of crisscross even some of the supply ducts so that we could only serve the spaces. So there was a lot of, I'll say, behind the scenes conflict for some of that as well. But we were able to work really closely with the architecture and the structural team and the integrated project team to help kind of solve those issues through our collective design knowledge.
What about the thermal comfort range of the occupants? Did that ever come up during the project, and how did that go with the client?
That did come up. Again, we presented sort of an expanded thermal comfort range in some areas that were less sensitive to that, to the client as an operational energy saving strategy. So certain areas that were more transitional, obviously you want to be pretty comfortable if you're sitting in a classroom for hours, or if you're in some type of research engineering environment. But the maker space in the machine shop, as well as kind of the flex lobby space and more of the transitional spaces, we actually increased the temperature range there. And operable windows were added too, to really more as an amenity to allow some of that additional comfort to be provided for user control.
Awesome. All right, you guys. Well, I think we're a little bit over, and that was a really awesome conversation. I really want to thank all of our presenters today for the great content and all the great questions from everybody. This has been an awesome lecture. Really appreciate everybody's time and really happy to be a part of this. So thanks, everyone.
Well, thanks for having us, Ben. Really appreciate it. It's a lot of fun.
Yeah, thanks, Dan.
Great presentation.
Yeah, this is awesome. Thank you, guys.
Very
We
great
really appreciate
presentation.
it.
Yeah.
Thanks so much.
We have
Nice, thank you.
we recorded the presentation, and we will put a message in with a link on our website. We'll talk about that during tomorrow's Thursday at 3, so people can access that. If we also have, we do a weekly, AI Oregon does a weekly virtual happy hour, Fridays at 4. This week, we're going to have some of the AI national political advocacy staff with the state and the federal level joining us, and we're going to talk about how the climate of how COVID is going to affect the political landscape in both Oregon and nationally, and affecting maybe the other priorities that we have, whether it's climate action, resiliency, or other things, and how we as a group of architects can might require us to change our approach to our legislative affairs activities within this context. So hopefully you join us. Go to the website, go to the events page, register for the virtual happy hour. We're doing it every week, and this week's topic will be an interesting one. So.
All right. Awesome. Thanks, everyone.
Thank you.
Thank you.
Thanks all.
Thanks, everybody.
Thanks.
All right.
Have a great evening.
Have a great evening.